Hello, guys and gals. We are going to go over AP Chemistry, Chapter 4 on chemical quantities. Section 1 of Chapter 4 goes over climate change and the production of carbon dioxide from the burning of fossil fuels. Read that on your own. It's just one short page. Section 2 is where we're going to begin today. It is about stoichiometry. So for our non-chemistry analogy, we have the equation for the perfect s'more. 1 marshmallow plus 2 squares of chocolate plus 2 graham cracker halves makes 1 perfect s'more. So suppose that you get to camp and you find that you have a bag of 15 marshmallows, 2 packs of chocolate, each containing 10 of these squares, and half a box of graham crackers, which is about 25 whole graham crackers. How many perfect s'mores can you make? Okay, so to go through and solve problem 1, we are going to figure out how many final products we can make from each of our reactants. So the 15 marshmallows, I'm going to put MM for marshmallows, can make 15 s'mores. Okay, so we just went from our reactant to our product, and I used what's called the mole ratio, the ratio of our reactant to our product, which is 1:1, to figure out how much product I could potentially make. Okay, so for the second one, I have 2 packs of chocolate, and they each have 10 squares. That's a total of 20 squares of chocolate. Squares of chocolate. Okay, and that we would use the ratio of 2:1, meaning I need 2 of these. Okay, so mathematically, I would actually multiply it by, I need 2 squares of chocolate. That says chocolate. I know you guys can read that. Over 1 s'more. So I'm dividing by 2. And this stuff is easy to do in our heads, but you guys know that we're not going to have nice, pretty numbers like 20 and 2:1 for our actual chemistry example. So anyways, we would divide by 2, and that would lead us to 10 s'mores. Okay, and then last but not least, our graham crackers. If I have 25 whole graham crackers, and I need 2 halves, which is basically 1 whole, I could make 25 s'mores from that. Okay, so I have all of these ingredients, and my job is to figure out how many s'mores can I actually make. Well, if I had used up all of the marshmallows, I would make 15. If I use all of the chocolate, I make 10. And if I used up all the graham crackers, I would make 25. So what is my actual answer? How many can I make? It's the smallest number. And this is exactly what we're going to see in our chemistry example coming up. So the amount that you can make is, you have to do the math as many times as there are reactants. Thankfully, there's usually only 2 reactants. So we figure out how many can I make from each one. The smaller number is how many you can actually make. Okay, number 2, that was number 1. So my answer is 10. Number 2, which ingredient is limiting your recipe? Okay, so to figure out the limiting reactant, we are going to go with whichever one makes the smallest amount. That is the one we run out of, and that limits how much product we can make. So that's our chocolate. So the chocolate is my limiting reactant. Number 3, which ingredients are present in excess amounts? The other 2 are present in excess amounts. So the marshmallows, and the graham crackers are present in excess amounts. So that means after I make my 10 perfect s'mores, I'm going to have marshmallows and graham crackers left over, which sometimes people just want to eat marshmallows or graham crackers, so that would work out. But anyways, after we make our s'mores, we have some of those left. That means they're in excess. And usually in a real chemistry problem, the excess reactants, that just means that you have plenty of it. It's not going to limit your product. So basically we can ignore the marshmallows and graham crackers and only worry about the chocolate, because that's the one that's going to limit how much we can make. All right, number 4, how much of each excess reactant will be left over? And more importantly, what mathematical steps did you take to answer this question? All right, to figure out how much we have left over, we have to use this number, which is how many we can actually make. And if I make this much product, we have to work backwards and figure out how many of my original marshmallows did I use. And then we're going to use subtraction to figure it out. So let's do that. If I make 10 s'mores, if 10 s'mores are made, that means that I used 10 marshmallows. Let's put MM for marshmallow. And I need 2 halves, so that means I would use 10 halves. Can we just call that, 20 halves. Let's go back. We are using 10 full crackers. Let's keep it as the full cracker. 10 full crackers, because that's what we were given, was how many full crackers we have. Okay, so we figured out how much of each of these we used, and now we're going to use subtraction to figure out how much I would have left. Okay, so I started with 15 marshmallows. Okay, so to figure out how much we have left, it would be 15 minus 10 is 5 marshmallows left over. Okay, and then for our graham crackers, I had 25 whole ones, and I've only used 10 whole to make my 10 s'mores. So that means I have 15 whole, I'm just gonna write crackers, left. If they wanted it in halves, we would just double that. We would have 30 halves left over. Okay, so that's how we figure out how much of my excess reactants are left. We have to assume that we make the maximum number possible, so that was 10, figure out how much we would have used of our excess, and then subtract how much we used from the original amount to figure out how much is left. Okay, that is pretty complicated when it gets to a real problem. So let's look at an actual molecule stoichiometry problem. Okay, so we have the equation for making water from hydrogen and oxygen, and we have our little molecules to kind of give you a visual of what's going on. So the oxygen bond has been broken. We have 2 oxygens that are now separate, and the hydrogen bonds have been broken, and we've attached the hydrogens onto each water. So we have 2 hydrogens on this oxygen, 2 hydrogens on this oxygen. So we've broken 1, 2, 3 bonds, and we made 1, 2, 3, 4 bonds over here. Okay, so the ratio here is going to be 1 oxygen for every 2 hydrogens, or we can look at the ratio of oxygen to water. 1 oxygen molecule made 2 molecules of water, or we can look at this one to this one. 2 molecules of hydrogen make 2 molecules of water. And also, we're going to talk in a second that here I've put the pictures of the molecules, but if I have a whole mole of oxygen, it's the same ratio. I will need 2 moles of hydrogen, and that will produce 2 moles of water. So the ratios here of 1 to 2 to 2, they're going to apply whether you're talking about individual molecules or whether you're talking about a whole mole of those molecules. Okay, so let's suppose that we have a balloon filled with 1.25 moles of hydrogen. That's a big balloon because 1 mole is 22.4 liters. And you add a spark, the balloon explodes to create gaseous water until all the hydrogen is consumed. I can answer number 2 just based on the wording of that question. Let's see if you guys can in a second. Okay, so first of all, number 1, how many moles of water did you make? I'm going to write my given. You guys know this. You always start with writing the given number and the given units. And I'm going to put the given molecule. It's hydrogen gas. Okay. And we want to figure out how many moles of water. Sorry about that. How many moles of water? So I want to cancel out moles of hydrogen, moles of H2, and I want to find out how many moles of H2O I have made. Put this over 1. The numbers that go here and here, this is our mole ratio. It's a ratio, which is a fraction of moles of water to moles of hydrogen. And this is your given goes on the bottom. The one we're looking for goes on the top. And the numbers come from my balanced equation over here. So this 2 in front of the hydrogen and the 2 in front of the H2O are what go up here and down here. This is a 2. So it's a 2-to-2 ratio, which can cancel to a 1-to-1 ratio. And basically, if I have 1.25 moles of hydrogen, I will make 1.25 moles of H2O. Okay, so this is number 1. Okay, and number 2, what is my limiting reactant? Well, it says that all the hydrogen is consumed, and that's the definition of a limiting reactant. It runs out. It's all used up, it runs out, and we can't make any more. So hydrogen is going to be, hydrogen gas is going to be my limiting reactant. I'm going to put LR for limiting reactant. Okay. It also tells you that the balloon explodes. Oh, well, it's reacting with oxygen. It doesn't say anything about the oxygen. We'll come back to that. Which reactant is present in excess amounts? Well, since it didn't mention the oxygen, it just said that you have a balloon. We're going to assume that it's in air. And remember that air is about 21% oxygen. So the hydrogen that's burning is burning in air, which means we don't run out of oxygen in the air. This is my excess reactant. Okay, and number 4, why can I not do the same thing I did with the marshmallows? Why can I not calculate how much oxygen we have left? Okay, the reason we can't calculate that is because we don't know the starting concentration. Okay, we don't know the beginning, which is also called the initial, or the ending concentration or amount of O2. Therefore, we can't find how much was used up. All right. Mole ratios. Here's just a summary of mole ratios. So that's what we were using over here. This is our mole ratio. The ratio of marshmallows to graham crackers or hydrogen to oxygen is called a mole ratio. They're written as fractions, and you can have 1 marshmallow over 2 graham crackers, or you can have the inverse of that, 2 graham crackers over 1 marshmallow. Both are ratios, and we're going to choose which one we want to use based on what the given is. Down here, 1 mole of oxygen to 2 moles of hydrogen, or 2 moles of hydrogen to 1 mole of oxygen. These are the ratios from the formation of water, and we're going to decide. Over here, we didn't use either of those. We used the ratio of hydrogen to water, which was 2-to-2, based on the balanced equation. Mole ratios are used to convert from one species in a reaction to another. Notice it didn't say reactants or products because it can be anything. Like this would be reactant to reactant. Over here, we had reactant to product. Okay, and here we also have reactant to reactant. So you can choose anything from the balanced equation and compare one to another. That's why it uses the word species. And we can make a fraction. We call those mole ratios. The mole ratio you use should have the given compound or element on the bottom and the unknown on the top. Let's do another example. Okay, this is a lot bigger numbers here. We have 2 octane molecules. That's these long hydrocarbons here. There are 8 carbons bonded to 18 hydrogens on each one, and they are going to react with 25 oxygen molecules from the air to produce 16 carbon dioxide. So these 2 octanes make 16 moles or molecules of carbon dioxide and 18 waters. Okay, the balanced equation shows that 16 CO2 molecules are produced for every 2 moles molecules of octane burned, we can extend this numerical relationship between molecules to the amount of moles because the coefficients in a chemical equation specify the relative amounts in moles of each substance involved in the reaction. The numerical relationships between chemical amounts in a balanced equation are called reaction stoichiometry. So this work of changing from octane to carbon dioxide produced, we use the numerical relationship of 2 to 16 as that's stoichiometry. Okay, so everything we've been doing up here, changing from one species in a reaction to another, is stoichiometry. All right, the balanced equation for combustion is written again without all of the little molecules pictured. Suppose that we burn 22 moles of octane. How many moles of CO2 form? So we're going to use this mole ratio to solve the problem. Okay, so for this example, we write the given. That's 22.0 moles of octane over 1. And what it asked us for was the carbon dioxide. So we're going to put moles of CO2 on the top. And we want this octane to go away. So moles of octane go on the bottom. And the numbers for this ratio come from the balanced equation over here. So it's 2 to 16, 2 down here, 16 up here. And so mathematically, we're going to multiply 22 and 16, divide by 2 times 1, which is just dividing by 2, and we get 176 moles of CO2. So from just 22 moles of octane, we get 176 moles of CO2. Okay, that's a really ugly C. All right, so this is using a mole ratio. However, in the lab, the mass of a substance in a lab is measured in grams. This can be converted to moles using the molar mass of the substance. You guys remember value of the moles. We can go from grams to moles by dividing by the molar mass. A more relevant question would be, if the world burns the equivalent of 3.7 times 10 to the 15 grams, because we're measuring the amount in grams of octane per year, what mass of carbon dioxide is emitted? So, that actually helps. Almost always for these type of problems on the AP test, we have a grams to grams problem. So what we did over here was a moles of A to moles of B. It's one step. It's a mole ratio problem. We don't usually have those because we measure grams in the lab, and then we have our product that we also measure in grams. Okay, so it's almost always this 3-step process of taking the grams of A and converting it to moles of A, and then moles of A to moles of B, multiplied by the mole ratio, and then moles of B back to grams by multiplying by its molar mass. Okay, so we're going to do a few of these where we go through the whole process, grams of A to grams of B. So for this one, I have it solved out here. We're going to start with our given. Okay, let's write the given over here. 3.7 times 10 to the 15th grams of octane, that's C8H18. And we're trying to change that to moles. So I need to divide by the molar mass, the grams of octane in 1 mole of octane. How many grams is that? We add up our 8 carbons and our 18 hydrogens, and we get 114.22. Okay, and then I'm at moles of A. A is just whatever compound is given, so this is my A. This is the mole ratio, the next step. The given goes on the bottom. Moles of A over moles of our unknown, under moles of the unknown, and we want CO2. Okay, and the ratio, we just did this. It's 16 carbon dioxides for every 2 octanes. And then last but not least, we wanted the mass of carbon dioxide. So I have to get rid of these moles. So I'm going to put 1 mole of CO2 weighs how much? That is 44.01 grams of CO2. Okay, and so if we take, this is over 1. We take all the top numbers and multiply them together. We divide by the bottom numbers, and we should get 1.1 times 10 to the 16th power. That looks like a 16. That's a 10. Okay, and that's how many grams of CO2 are produced. Notice that we had two significant figures here, so we end with 2 at the end of the problem. All right, let's look at example 4.1. This is on page 143 in your textbook. This is the equation for photosynthesis. 6 carbon dioxides plus 6 waters makes 6 oxygens and 1 molecule of glucose. Suppose that a plant consumes, so example 4.1, suppose that it consumes, let's write the given, 37.8 grams of, that just says C. It's supposed to be carbon dioxide. I'll fix that. This is CO2 in 1 week. Okay, I can write week down here if I wanted, but I'm not going to. We are going to get rid of these grams of carbon dioxide, grams of CO2, change it to moles. This is the first step in our value of the moles. If I go over here, we've changed from grams of carbon dioxide to moles of carbon dioxide by dividing by the molar mass. Okay, so over here, we're going to divide by the molar mass. And then the next step would be my mole ratio, where I have the given, that's carbon dioxide on the bottom, and the unknown, that's my glucose, goes on the top. Okay, so I have moles of CO2, moles of C6H12O6, and the ratio of those is 6 to 1, 6 of these to 1 of these. And now I'm at moles of B, so I've used my molar mass here to convert it to moles. I've used the mole ratio to change it to moles of B, and the last step would be moles of B to grams of B, and I do that by multiplying by the molar mass because I need moles on the bottom and grams on the top to get to my final answer. Okay, C6H12O6. The molar mass of glucose is 180.18. And so you multiply these two, divide by these, and we get 25.8 grams of C6H12O6. So in 1 week, this is how much glucose that particular plant can make. Right? A few definitions. The limiting reactant is the reactant that's completely consumed in a chemical reaction, and it limits the amount of product we can make. The chocolate that ran out and therefore limits the s'mores was the limiting reactant from that example. The excess reactant is left over after the limiting reactant is gone. It does not limit the product. So my marshmallows and my graham crackers were my excess reactants. And usually the excess reactants, again, we kind of don't worry about them usually. Theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of the limiting reactant. This is calculated, and it's assuming 100% of the limiting reactant is used up. So what we just calculated, how much glucose or how much carbon dioxide could be made, those are the theoretical yields. That would mean that every single octane was completely converted to carbon dioxide, or every single carbon dioxide that was there was converted into glucose. Now we know that we do not live in this perfect world where every single molecule of CO2 is going to change into this glucose. So we usually, okay, not always, but we usually get numbers that are less than 100% because not every single molecule is going to react, okay? The actual yield, how much you actually produce, you would have to collect the glucose from that plant and see how much was actually made, or you would have to collect the carbon dioxide, which this would kind of be impossible, and measure how much was actually made. So it's only found either in the lab by measuring, or usually it's just given in the problem. It'll say this is how much you actually made. So the plant, let's pretend, actually made 24.0 grams. So they would have to tell you the actual was 24.0 grams. And I just made that number up of glucose. Okay. Then from the theoretical that we calculated and the actual, we can calculate the percent yield by taking the actual over the theoretical and multiplying it by 100.